is there. So there is threaded portion, there is unthreaded portion. Wait. So this will be AT, this is AD, and these we can assume that this is, and that there is a bolt here. We can basically assume that there is this is LD, which is not threaded, LT, which is threaded, right? And basically this is what you have to see here. The bolt compliance will be, you know, that delta is equal to PL over AE, right? So K is nothing but P is equal to K delta. So basically K is if you see, let me just say, K is AE over L, right? AE over L, sorry, AE over L. So in this case, what happens? There are two portions. There is a spring, which is one spring which corresponds to the bolted one, the threaded one, and other one is unthreaded one. So basically, I can say KD is unthreaded. So KD is equal to AD. E is same, material is same, so it doesn't really matter. ADE by, you have what is it called? What is the length of this? Is LD, right? And what is the thread portion? KT will be AT times E divided by LT. This we did in the last class. Now if we want to see this, these are in series, right? So basically series means that the total stiffness will be 1 by KD plus 1 over KT. So now if I do that, so 1 over K, this is actual complete bolt, 1 over KB is equal to L divided by, so basically it will be LD divided by AD E, right, plus LT divided by AT E. Now if you do this, 1 over KB, you will get AD AT E, and what do you get here? You will get ADE. If you do this, you will get AT E LD, and what will you get here? You will get AD E LT, right? So now if you go ahead and do this, you will get yes, AD AT E, so ADE ATE, and you'll get LD by ADE. Let's just see that AD by LTE. So LT ADE. So 1 by numerator, yeah, where
in the numerator there wouldn't be an E.
In the numerator, what you will get?
There wouldn't be an E. So 1 by KB is equal to AT.
Yeah. So there has to be a E square. There would the top should have a E square there.
Yeah. Or no E.
No. So this should have a E square here somewhere. So if you do that, that's what. So because you are putting this E, right? So this has to be E square, because if you see that LLTE, so that there will be an E in the top, right? So KB will be equal to, if you see, AD. So basically you will get AD ATE. If you do that, AT LD plus ADLT. So this is what you get for the stiffness of the bolt. Okay, this pretty much we had discussed in the last class. So what I'll do is I will let it be here, and then we go from this to the other thing. Okay. So this is how you compute the bolt stiffness. Now the issue is, why do you need to worry about this bolt stiffness? Why do you think bolt stiffness is important? Why do we calculate this in the first place? Why do you calculate this in the first place? This bolt stiffness. Anybody? Is it required? Any answers? Is it required? Why do you need to worry about this bolt stiffness? And then I'll also talk about the stiffness of your members which are being squeezed in this. Why would it be important at all? Any answers? Any guesses? Yes, to see how it deflects under the load is fine. Typically, what happens is these structures, right? We need to know the stiffness because their structural dynamics also responds to that. You need to know because there are additional compliances and you need a stiffer member. The moment you're bolting, right, your bolting will have lower stiffnesses. Of course, it will deflect under the load. That we need to know because these will be these are joint and the stiffness is lower than as if it were welded or permanently joined or fully bonded. So that's one aspect that you want to understand what kind of deflections would be there. Other than that, this will also affect the structural dynamics. So if we have compliances, lower compliances means we need to understand what compliances would be there so that a system, right, because these will be subject to cyclic loadings, so they can also vibrate. So we also need to estimate what kind of stiffness this system has. So that also is one way to kind of estimate what kind of stiffnesses will be there here. Okay. So that's one thing. Then what you do is typically when you tighten the material, there would be, this is how you calculate, there is LD. So L is the material of all squeeze between the bolt face and the face of the nut. So all the material if you see which is squeezed, which will include the washer as well. And if you see, this is the total, L is the length of total material being squeezed. And L typically is, if it is, and then there can be two ways, right? One can be there is a bolt, the other can be it is a threaded portion. So you have a thread and you tighten the material in the thread. In both cases, there are different L's. So here you know that it is easy to compute L because L will be LD plus LT. So threaded portion is LT, unthreaded portion is LD. So the sum of this will be total length L. And all this you can find in Shigley 832, 833, where washer thicknesses are known. So if you are using something like this, in that case, if there is this is a threaded joint. So this is tapped and you're tightening the thing in the tapped thing. So in this portion you have to determine L. The way to determine L would be which is the effective screw grip where the material is being squeezed, is H, which is the so this one would be just, this will be just purely drilled. There will be no threads here. So this portion is actually through hole. Now this will be thread. The bottom portion is threaded. Right. Now what happens is, of course, the washer H, right? So H plus, if you see H plus, so this is T1 and this is T2. So actual compression is if my T2 is less than the diameter of the bolt, T2 meaning the thickness in which it is getting screwed is less than the diameter, then it HT, this is H plus T2 by 2. And if it is larger than the diameter of the bolt, then it is H plus D by 2. So the portion which actually is under compression is more than the typically it is more than H, which is the washer plus the top layer, and a portion of the thread portion also comes into the effective grip. So that also gets a little bit compressed. The reason why I'm explaining you all this is because we'll need this to find the compliances of the plates also. If you're using the plates, there will be compliances of the plates also. So all these concepts will be needed. We'll solve a problem as well today. Okay. And then fastener length, if you want to see, typically L is if you know, L is typically 1.5 times of here's the table. I'll just actually show you the table so that way you are. I think we had the table somewhere here. Let me just pull it out. Oh, I haven't put it. So what I will do is I'll share this with you. I think I have it here. Just 1 second. Can you see this? So if you see your there are data points for what will be the length of the diameter of the nominal pitch. Length we'll see. Okay, let me just see what is the length for a given diameter. So typically these are the total length of the bolts for a metric thread is 2D plus 6. This is the thread length actually. Let me see the total length. How do you find it? Total length also you can find it. Yes. So total length, if you see, this is the total length. Total length L is figure A. You have total length L. L is typically fastener length. You can use the table A17. Let me just go to table A17. Just show you what A7 how fastener length is calculated. Total length. A17. A19. 18. Yes, so A17. So fastener lengths, if you want, preferred sizes are series, fraction of inches, quarter, half inches. So these are the sizes which you get, and let me just find out where the fastener lengths are there. Decimal inches. So these are the sizes which of the boards which are available in the market. This is the diameter actually, but the lengths also should be there. The first choice, Reynolds number. 10. Let me just go ahead and see what are the lengths. So different lengths are available, but I want to understand what would be the typical length you have. Okay. So let me just have a look at it here. So one example is that if you have, so total length in this case, if you see, so length is actually specified in some cases. So in this case, this is 3 times the, this is 3 times the diameter, but typically you can get any length. What is H in the effective screw grip? Okay, let me just show you what H is. So basically I wanted to show you what sizes can vary, right? You can have any length of bolt. I wanted to look at it. What are typical lengths? Because depending upon, for same M6, you can get different sizes. So I was looking for what kind of sizes you get in the market. So typically, I think the maximum what it shows is you can get 1:10 kind of ratios, not more than that. So there is some absolute limit which you can get, and you get in some sizes. So this is typically you are getting 1:3, but you get different sizes of. So your length is something that you can get. It's a free variable, but it comes in separate some sizes. So actually, let me just go ahead and show you. So there are some sizes which you will get. So 0.5 you will get in, say, 1 inch, 1.5 inch, 2 inch. You'll not get all the lengths. Of course, you can grind it and make it whatever size you need. But let me just first show you that. So I wanted to look at whether there are some specific sizes which you can go and look at it. So I think this Reynolds number gives you that idea. But you can get any length of the bolt. That is a variable. Probably it depends on the diameter. Some multiplication of diameter you will get. So this is something which somebody was asking. What is H? So H basically means the size of the plate. So basically what is happening here is, let me just unshare this. I think then you'll be fine. Let me just unshare it from here. Okay. Let me share this. Okay. So let me do this. Okay. So basically, so this is what you're asking. What is this H, right? So this H in a screw grip, if you want, in a tapped thing, this H is the top plate plus washer thickness. Both this combined, because this top plate is not threaded. Only the bottom plate is threaded. The top plate is just through hole. So this one actually is there. This plate is there, and then there is a washer. So the height, the thicknesses of the washer and the top and the plate combined is basically your H. Okay. So this is what, how do you estimate the effective grip? So here it is basically, sorry, here it is H, which is the thickness of the washer and the actual plate, plus something T/2 or D/2 in this case. And in this case, it's very easy. Whatever is being compressed, which is basically this plate and the washer, everything combined would basically give you the effective grip length. And we'll use this concept in figuring some things out. And then L is greater than L plus H. All this you could look at it. L has to be greater than L plus H because otherwise it will not screw. So you know what you are. So if you have to size a screw, the way you will basically you will get is you need the total thing which is getting compressed plus the height of the bolt, and plus you need something extra. So this is total thing which is getting compressed plus the bolt height. You should have something more than that, some extra left, few threads left to be able to do that, right? So these are the things which you need to have to size the what kind of bolt you have to use. You need to know what is the effective gripping length, what is the effective grip length, what you are, which basically means what you are compressing plus the bolt height of the bolt, and it should be more than that. Okay, that's something which is no brainer, right? That you don't have to worry about. Right? Any questions here? And then we'll go to the next thing. So this is something common sense, right? You have to have the bolts larger than what you are gripping, the total effective grip plus the thickness of the bolt, right? Okay, sounds good. Then you have threaded length LT. For inch series, it's basically 2D plus 1/4. This should be threaded. If it is less than 6 inches, and if it is more than 6 inches, then you do 2D plus 1.4. That's the thread length typically. Okay. So basically thread length is only there for bolting, right? That's what you need. In metric, the same thing. You have 6 mm less than 125. Between 180 to 200, you have 12 mm. 2D plus 12 mm. And if you have greater than 200 mm length, then you get 2D plus 25 mm. Okay, these are something which you have to look, because these will be there. These are standards. So if you go to the market, this is all you get. So you don't have to worry too much about it. These things people have decided after developing standards. Okay. Now what we will do is we'll try to figure out how do you do the member stiffness. Now the member itself, right? If I'm bolting, it will have finite stiffness. So if I apply load, it will deflect, as you said, right? But how much will it deflect? I have to figure it out, right? Because for design requirement, if I'm bolting, I also want finite stiffness so that my structure is rigid enough after bolting. So how do I estimate what will be the stiffness of various members I do? So basically what will happen is I can assume this to be something like this. I have a bolt. So let's say a bolt head has some finite width W, which is typically W is equal to 1.5 times D. The maximum width of the bolt is 1.5 times the diameter. Now this is what is compressing it. Now I have a fundamental question here. So what will be the total pressure at the top? What will be the pressure acting? The area where the pressure will be acting would be just the W, right? At top, W will be the total area, I would say maximum diameter, so to say, right? Will be the total diameter on which the pressure is acting. Here it is 0, P is equal to 0. Here P is equal to 0. Because of tightening the bolt, the entire pressure is acting only in the W diameter. Now tell me how the pressure will vary from the bottom of the bolt. So Where do you think the pressure is maximum? At what location? Any answers? I'm tightening these two members. Let's assume, right? I have this layer 1 and layer 2. I'm tightening with a bolt. I'm tightening with a bolt. Here there is the sorry. Here there is a bolt head, and here there is a nut. Now, in this location, where would be the maximum pressure? Will it be at the top? Will it be at the bottom? Will it be at the center? Where will it be? Where will the maximum pressure lie? Any answers? Anybody? Will it be at the top? So I have a bolt head and I have a nut. I've tightened it, right? Where do you think in these two plates which are being tightened by a bolt, where will be the maximum pressure? Anybody? Where will the maximum pressure lie? Anybody? I'm tightening. Where do you think the maximum pressure would be? Top, bottom, center, where will the maximum pressure be there? Any guesses? Near the nut or near the bolt head, right? Or only near the nut? Isn't the bolt head also compressing the material as much as the nut? So there are two answers which people are giving. At the top, near the head, or near the nut. Right? An ideal world, they should be the same, right? Both are compressing by equal amounts. Right? So your pressure, if you would like to imagine how it will be, it should be maximum here at both locations. Imagine my bolt and my nut having the same footprint, maybe same dia, right? If it is there, my bolt head and my nut typically has, imagining that I have the same cross sectional area. If I have, then it will pretty much be symmetric, right? And what will happen if we go further away from it? What do you think will happen? If we go further away from it, will it increase, decrease? What will happen? If I go down say at location 3, will the pressure be lower or higher? As I grow away from the nut or the bolt, it will be lower, right? So what it basically means, if the pressure is lower, then since force is the same, right? If I make a free body diagram, right? If I make a free body diagram of, say, how the pressure distribution in the member takes place, right? So what will happen is your area will keep on increasing. So your area which is under effective pressure would be like a frustum. It will be right of the size of the bolt head here, and then it will tend to have a frustum. It will tend to have something like this. Everybody agrees? Everybody agrees to this? So as I go down, it will spread out because pressure decreases. So effective area where the pressure is acting will increase because the force has to be same. If I do a free body diagram, I balance the force. So the force will still be the same. Whatever this is applying, whatever the bolt is applying, the internal force, the internal pressure which is acting here should be the same. And on this face, there will be pressure acting. On this force, there will be pressure acting like this. So pressure will be lower, but it will act in a larger area, right? That being said, if you get that concept right, then what we'll do is we'll set out to formulate something here. Let's try to formulate something. Very interesting formulation. I'll go ahead and I'll try to formulate this. Remember this. Okay, let me formulate something like this. Basically, what I say is, let me formulate something like this. I assume that this is my bolt head. Let's assume this is my bolt head. I'll make these two. This is a solid line. So this is in the material. This is in the material. This is where my bolt is. Right. So this is where bolt head is. Let's assume that if this area which comes, it's like a nice frustum it's like a cone frustum. And I say the half angle is alpha, right? And this is my bolt dia. This is my bolt dia D. So this area is hollow, right? And this area is hollow right here, the diameter D, and the bolt goes through this. So if I assume that I am at X distance from top, I take a strip dx here. I go X distance from top, right? So if I understand it right, my d delta, if I want to understand the incremental deflection due to this strip, will be what? P, whatever is the load which is there, whatever load I am applying, dx, PL over AE, right? You remember delta is equal to PL over AE, right? So this will be P dx over AE, right? Now, can somebody tell me what is the area here? For the lack of a better thing, let me delete something here, because the actual area which is there is only this much. This is the bolt area, right? So there's nothing there. So only there is a strip. So how do I find what the area is there? Any ideas what will be the area? Can somebody help me with the area? What will be the area? The area will be, so if the bolt diameter, if this is diameter capital D, where my bolt sits, capital D, right? This is capital D. So this will be, so if I want to understand what is the radius here, so it will be, this is X, this is alpha, right? So what is this distance? Right here? X tan alpha, right? So this is X tan alpha, this distance which has been highlighted, X tan alpha plus, and this distance, if you see here, if this distance you want to understand, this distance is D by 2, right? Plus D by 2, right? So this is the outer radius, right? If I do pi, this is my X tan alpha plus D by 2 is this whole square is the outer D by 2 plus X tan alpha is the outer radius. It is this distance. It is this distance. This is the outer radius, right? And the inner radius will be what? Inner radius will be what? D by 2 whole square. right? Agreed? Yes or no? Right? So this will be my d delta. Now, how do I find out what will be total delta? How do I find that out? Tell me. Let me just do this. This is a better way to write it. Okay. Everybody agrees to this, right? What do I do next? How do I find what will be the total deflection? Right? If I know the total thickness, can I find out what will be the deflections? Yes or no? Let me do this. Let me do this. Let me insert a few more slides here. Let me keep layout blank. Blank. Okay. So let me do first this. Let me just write this out. D delta is equal to P dx over A, we know is outer radius. Outer radius is nothing but x tan alpha plus d by 2 whole square minus d by 2 whole square. So this is what we get. P by, and then there should be another thing here, which should be E. This is A, this is dx. So if I want to integrate, delta should be 0 to t dx pi E x tan alpha plus d by 2 minus d by 2 times x plus tan alpha plus d by 2 minus d by 2. Everybody agrees to this? Right? Can you find out the integration for this? Can somebody tell me what do we get out of this? Any ideas? How do I find the what delta would be? Okay, so what I will do is, I know this is slightly difficult for me. So what I'll do is I'll go ahead and I'll share my usual Mathematica, and I will share the Mathematica with you. Okay. So this is what we figured it is. Right. So what it does is it actually gives me this definition. If I do integration 0 to t p dx pi e, I get this expression minus this. This is my solution for this. This is my solution right here. 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 Okay. Now, still don't like it. So what I will do is, I will ask it to do full simplify. I'll ask it to do full simplify. See, it simplifies. Oh, sorry. I'll have to do this shift because it stores a lot of these terms which I have actually calculated. So let me do this. Now you will get the nice formulation for this. Okay. So Just 1 second, my battery is low. Okay, sorry about that. The computer was about to die, so I had to do this. Okay. Okay. So you get this formulation as you ask it to simplify, it simplifies nicely here. It simplifies nicely. It says delta is equal to, I will just use this. Let me go ahead and shift to this one. Stop sharing this one. Okay. Okay. And let me reshare this. Okay. So basically what I said was, you get, let me just write out what we got from there. We got from there was, we got there is, what we got from there was, let me just write out what we got from there. We got 1 by pi e pi e pi e d sorry So 1 by pi e d, you get basically p cot alpha from this, from Mathematica, p cot alpha minus log minus d plus d cos alpha plus log d plus d cos alpha this one you get plus log d minus d. Okay, I'll just keep the same thing the way it is there, minus d plus d cos alpha plus 2t sin alpha 2t sin alpha minus log d plus d cos alpha cos alpha plus 2t sin alpha. You can simplify this. It's very simple to simplify. You can simplify this entire thing. This will turn out to be, if you do some stuff, you will basically get 1 over pi dE. You will get d. You will actually, you can very simply, you can do log. So this, if you sum log m plus n, it's a multiplicative thing. So what you will get is, you will get something like this. If you do the math, it's easy to do. You can just go ahead and do it. You will get log d plus d times d minus d plus 2t tan alpha divided by d minus d, d plus d plus 2t tan alpha. 2t tan alpha, 2t tan alpha. There is 2t tan alpha, 2t tan alpha. This. It will come nice. Just do some manipulation, you will get that. Okay. So what I'll do is, I'll move on to this, this, and then I think, let me just open the. Okay. What I'll do is, I'll just do this. So you'll get something like this. Pi ed tan alpha. Yeah, here there is another tan alpha here actually. Yeah. So basically you'll get this term. Delta is equal to P by pi ed tan alpha ln 2 tan alpha plus d minus d, d plus d. So you will get this term right here. This term right here. And K is equal to P by delta. So now you have delta, so you can basically figure out what will be K. K turns out to be very nice, pi e d tan alpha. It comes out to be like this. Very nice relationship. So now what we have to do is, if we have 30 degree, alpha is 30 degree, and so we can basically find out what would be the stiffness value. And what we can do is, you can have combined all these frustra from top to bottom. So if it is symmetric, it's very easy. If it's symmetric, what you do is, it's just k by 2, and L is nothing but L is basically the grip length, which is there. So basically what you can do is, you can say, instead of L is basically go ahead, it is something. So basically what you do is, L is just the material thickness, simple material thickness. So what you do is, you just go ahead and this relationship you have K. Here you just put K over 2, because you will have, just give me a minute, what I'll do is. So L is just thickness of one layer. So this will be equal to K by 2. Just 1 second. So let me show this here. So this K is, sorry. So since you say that stiffness of the member is K1, K2, K3, so if you have, say, n number of members also, if you have say 2 members, it's very easy. Just 1 second, let me do this. So okay, so this is, if you see, sorry, you have something like this. If I am putting a bolt here, something like this, let's say the bolt plus washer, something like this here, something like this here. So basically all my compression will be symmetric on one side like this, other side like this. It's like a symmetric thing. So if this is if it's 2T, if you see, this is T and this is T, right? I say 2T tan alpha. 2T tan alpha, right? So this 2T will be, if I assume 2T is equal to L, even if I have multiple layers, even if I have, say, 4 layer, this will be always symmetric. This will be always symmetric. So this solution, if you see, will be one same thing will be there, right? Say if K1 is equal to K2 will be similar. So the stiffness on top is K1, bottom is, if the material is same, K1 will be equal to same, and 1 by Km is equal to 1 by K1 plus 1 by K2, and if the material is same, it will be 1 over 2K. So all you have to do is Km will be equal to K by 2, and this is true for any layer. 1 layer, 2 layer, 3 layer, 4 layer, it doesn't matter. It will be true for any layer, any number of layers. Do you get this or not? So if I have 2 layers, then also this is true. This equation is true. But if I have multiple layers, then also this equation is true. Do you get this or not? See, if I have 2 layers, then also the distribution will be like this. If I have 4 layers, even unsymmetric, then also, if 3 layers, then also the distribution is like this. The present distribution is independent of number of layers you have. Do you get this? So this Km will always be this, regardless if the material is same. If the material is same, you'll always get. I'm solving this for two layers, right? But even if I have n number of layers, same material, I will always get this equation. How many people agree with me? So I'm saying that this formulation of Km, which I showed with K1 plus K2, right? If I assume this is 2 layer, this is correct, right? Everybody agrees my 2T, this is 2T tan alpha, right? So this 2T will become L. There are 2 layers T plus T. Now I claim that imagine there is 3 layer T by 3 plus T by 3 plus T by 3. T by 3, T by 3, or let's say here TT, right? So let me say that instead of TT, 2T, this is T plus T plus T. I still say that this is correct. How many people agree with me? This result is still correct. Same thing you will get. Assuming this is L, T plus T L, here also there will be L. Because what will happen is my pressure will still be the same, regardless of how many layers are there. So I'll get exactly the same thing. Do you agree with me or not? Yes or no? So I'm saying that grip consists of any number of members. If there are same material, all you do is you use the same formulation which you use for two materials. So basically here it is 2t tan alpha, which we derived. I say just replace 2t is equal to L, and this will be true for any number of layers you have. The only requirement is that it should be same material, because regardless of how many layers are there, the pressure distribution would be the same, reverse thrust up, blowing from going out from top and again from bottom also spreading out, and it's evenly for a same material. It will be evenly distributed. Material different, if it material is also different, then also the same distribution will be there. That's what our assumption is. Even if I put something else, the distribution will still be the same dumbbell kind of shape. Oh, what is it called? Not dumbbell, but the same dholak shaped, right? Okay. So this concept you will need. That's what I'm trying to say. If I have face diameter dw, I can actually put this 1.5d here as dw, and I can get this relationship. Okay. Now I want to do this problem. Sorry, looks like I'm not shared. I want to do this problem. I say that there are two plates. I'm joining these two plates. You notice the bottom one is cast iron, the top one is steel. I have a steel washer, and then I have a bolt. Now I want to find out what will be the K1, what will be the stiffness of the bolt also, and what will the stiffness of the member. Stiffness of the members. How do I go ahead and find it? What do I do? How do I do this? Let me go ahead and do this. Okay. So I want to let me go ahead and blow this up a little bit. Okay, I have this member. Now, how many layers do we have here? Any answers? How many layers do we have in this? I'm tightening the bolt. There is a washer on top. There is a steel layer. So there is washer on top right here. So there is a washer. Can you see the cursor? Oh yeah, you can see the cursor. So there is a washer on top right here, top one. There is a steel thing in the, so this is number two. Number one is washer. Number two is steel layer in the top. The bottom one is, this one is cast iron. So there are three different items. Now, if I'm tightening it, how do you think the pressure will flare? How the pressure will come out to be? I want to find out, so what will be the three optimal sections which I should use? So there are three layers: steel washer, steel top plate, and cast iron plate. However, the pressure will be symmetric at the center line. I said, so that the concept which I gave you, right? Whether you have 2 layers, 3 layers, 4 layers, doesn't matter. You will get this nice this shape which you have, this one frustum and the other inverted frustum, right? This will always be symmetric. Now stiffnesses will be different because your moduli is different. Your moduli is different, so stiffness will be different, but the distribution of this pressure, regardless of the material, will be the same. So if I want to imagine this, right, my top layer, if I see my top, if you want to imagine the washer, if you see, is 0.095 inch thickness. Now I have a half-inch steel plate and quarter-inch, 3/4 inch cast iron. So total thing which is compressed is 0.95 plus 0.5 plus 0.75, right? So if I want to find out what is the total thing which is under compression, this turns out to be 0.095 plus 0.095 plus 0.5. What will that be? If you want to calculate it, it will be 0.095, which is the thickness of the washer, plus 0.5, which is the thickness of the top plate, plus 0.75. So it's 1.345, right? And this 1.345 is getting compressed. So the pressure distribution, as I said, will be regardless of what material you use, and it will be symmetric. Pressure will be symmetric. So what will happen is your pressure center line about which the symmetry is will lie exactly at half of this total height, which is basically 0.6725. So the total height is nothing but 0.95 plus half plus 3/4, all three combined, and this the line of symmetry is 0.6725. Now there is a very weird thing happening here. I have some cast iron. So I have three zones. The first one consists of spring of the washer. Washer is also steel, right? Washer is also steel. This top layer is also steel. So I have some portion which is basically the washer, and some portion of all the portion of steel, which is washer is 0.095 plus 0.095 plus half inch will be this point, which is basically if you want to understand what will that be, you can also find out it will be 0.6725 minus 0.0775, which is basically right from top of this point to where the steel ends. So this will be nothing, but if you want to find out, what I will do is, let me do this. Let me just first unset everything. I will unset everything and then we'll go from there. So what I say is this. So the top layer thickness is, if you see, this is the top layer. It comprises of the half inch plus 0.095. So if I say this distance, this should be exactly equal. Let me say T is equal to 0.5 plus 0.095. It should be both should come out to be same. 0.095. This T1 and T should be same. Let me just go ahead and first do this. Right? So the first layer, the first layer is the diameter starts from, if you look like here, there is the bolt head is basically, if you see DW, the entire the diameter which is there will be 1.5 times the diameter of the bolt. That's the initial size of the pressure. The bolt head is putting pressure right here. So D1 is 1.5 D. E1 is steel. This is the steel modulus. Alpha is 30 degree, and this T1, which is basically, I'll just say, which is the the steel washer plus the top layer of the steel, 0.095 plus 0.5. I'll just put here for lack of for confusion, I'll just put 0.095 to avoid confusion, 0.095 plus 0.5. That's my first section. This is my first section, which actually is just the washer and top plate, because they're all same material. I can club it as one. Then I have the cast iron portion, which sees positive pressure for some time, and then the reversal. So positive pressure, I will say K2. Here the initial diameter would be this, right from here to here, and the thickness will be 0.0775. And the bottom one, I can see reverse. It starts from again 0.5 times 1.5, which is basically 1.5. Assuming that the nut also has the same size, W is equal to 1.5 times diameter. So this will also be 1.5. 1.5 times 0.5 is 0.75. So this also is 0.75, and then it goes all the way till 0.6725. So I can use these three segments. I can use these three segments as K1, K2, and K3, and these will be in series. So let's find the first one. So the first one diameter is 0.5. I know that the bolt diameter is 1.5 times 0.75. W is 1.5 times D. So this will be the total area, which is the bolt head is compressing. So the bolt head diameter is this, right? Then I have 30 degree. Then I have the first one comprises of both the washer and the top layer. So washer is 0.095 and 0.5. And I use the same formula, nice formula here, pi ED, which we derived, right? Pi ED tan alpha, pi ED tan alpha, log T1 tan alpha. So basically, if you want, I can just bring the formula for a moment. K is equal to here. Pi ED tan alpha log 2t tan alpha plus d minus d, d plus d, 2 divided 2t tan alpha, d plus d. Exactly same formula I have written if you want to see here. Pi ED tan alpha log 2t tan alpha. So basically, that's the stiffness. So now I know T2. Oh, sorry, let's do with T1. So T1 is 0.95/05. Let me just do this. I run this cell, right? And then I run the 2T1. So I know T1, I know E1, I know D1. D1 is the top of the bolt, and small d is the diameter of the bolt, assuming that the diameter of the bolt and the hole is exactly flush. That's the assumption which you are making. And if you go ahead and run this, you get K1 is equal to 3.0827 10 to the power 7 pound per inch. I'm using some funky numbers because that's the numbers which I have. Then I have a thin cast iron frustum right here, very thin, which is 0.775. I need to find what will be the radius here. What will be the diameter here? The top diameter now is not the bolt, but this diameter right here. That's the top diameter. So when I have to use this diameter here, D2, this D2 is nothing but this dimension. I can just do simple geometry and find out that D2 is nothing but D1 plus 2 times. So basically you can find this out using simple geometry, assuming that if you want to show, I can actually show you. It's just so I know that let me just show it to you. So I think that should be fine. I'm sure this is very easy for you, but still what I do is I will okay. Just 1 second, give me. I'll just show what I meant to say. I meant to say that this I can find out. This I can find out by using by using simple geometry. I know this is alpha. I know this. I have to find this dimension. I know this dimension. This dimension is nothing but 0.75 by 2. So I can do simple geometry and find out what will be this dimension. That's all we have to do. Okay. I go back to the Mathematica now. Let me just do this. Let me go back to Mathematica. Okay. Okay. So that way I can find out what will be the D. For K2, I know that D, small d is still 0.5 because small d is this hollow section. Now the capital D, which I was using here as the dimension of bolt head D2, 1.5 times the bolt for the top, which is the dimension of the bolt head. Here it will become this dimension, right? The starting dimension for here, which we can calculate from simple geometry, and this turns out to be D1 plus 0.2595 tan alpha, and this is cast iron, and the thickness here is 0.775. So I can go ahead and find K2 is equal to this dimension, and I find out, oh sorry, I did something bad. I did not run this. Okay, so I run this shell and then cell and then run this cell. Okay. Let me do this 2.855. Okay. Let me do this first. I want to do unset it. If there are some issues with, I'll unset all the variables and then go ahead and run it again. This looks slightly hard to me for some reason. T2. Okay. What is not here? Tan alpha. Okay. I'll run this. Tan alpha. K1 is equal to tan alpha. I run this and I run this. So this is this I ran, and then let me run this now. Let me run this now. Okay. So basically the first one was 30.807. Let me just go ahead and see if our calculations are all right. I have the answers. So the other one is 30.80 10 to the power 6. The other one is 285. So the cast iron is, the stiffness is reasonably high for this, right, for K2. So basically the K1 turns out to be 30.80. This is what we got here. K2 turns out to be 285 10 to the power 6. Now the K3 also will be just the reverse of it. So I use the same values. D is equal to 0.5, and D2 I can find out what will be the center line. What is the center line here? That's very easy to find. Same concept you can put. D1 plus 0.59 tan alpha, right? So then I run this. I can find K2. I can find, let me do the K3 thing. K3. And let me run the K3. So K3 is 14.1. Now what I can do is, I know K1, K2, K3. I can just solve for Km. So Km turns out to be 9.3799 10 to the power 6. If I have to find the bolt, so if I assume all steel, if I have to find out all steel, it's very easy. All you do is you basically assume that it's all symmetric. So basically you put the steel properties here, D1 1.5D, and I use the same formula if you remember, 2T or L. So basically assume 2t, t is equal to 7.65. Use 2t or L. 2t is nothing but the total grip length, and get the entire formulation for steel. For steel, if the material is same all the way through, I told you all you can do is just take one section, right? One section, what you are doing, one section, just one section formulation, or basically, which basically means that you are assuming that your entire thing is symmetric, regardless of number of layers. So we have the different thickness of steel in the bottom, different thickness in the top, and the washer. But I'm assuming it to be perfectly symmetric, and use the same formula. All I am using is half T, or I can use L here. 2T is nothing but the entire grip length, whatever is being compressed between the bolts. So 2T is the 1.345, which is the total thing which is getting gripped. So basically I can do this and find out what the steel would be. So the steel stiffness turns out to be 14.6, and this is 9.37. So if I make it all steel, I get a stiffer joint, right? That's what was expected of it. Now I can also find out what the bolts is. So basically for bolt, I need AD, I need AT, I need LT, which is 2D plus 0.25. I showed you the formula there. I need L is equal to, I know L is equal to 1.5, which is given in the problem. And then I can find out what will be the threaded length, what is unthreaded LD, what is threaded LT, and I know the E. So I can find out what will be the bolt thickness. Let me just go ahead and run this cell and then run this cell, so I can find out what the bolt is. And then I can also find out what the entire thing would be. So entire thing is bolt and member is in series. So the total stiffness will be KB plus KM. That's it. Okay. We still have a few minutes. I think I solved this problem. If there are any questions, you can ask me right now. I know it is difficult to solve problems in this online business, but I still tried my level best to have a combination of Mathematica and this. So do you have any questions? Any questions about the formulation of the member stiffness? About this formulation or the problem which we did? Why did we split? Why do we assume that the pressure is always symmetric about the center line? Can you tell me why the pressure is symmetric about the center line, regardless of what the material is? Is that a good assumption? Anybody? Any questions you guys have, I'll be happy to answer now. I think we can take a few minutes, and then if you have any questions, I can answer. No questions at all?
So,
Yeah.
I had one question.
Yeah, go ahead. Yeah.
So in this we have assumed the head area to be equal to the nut area, right? And that is why
We are
the
assuming
distribution.
head is basically 1.5 times the diameter of the bolt.
Right. So, but how is it symmetric? Is because the nut area is also assumed to be the same, right?
Yes, yes. Nut and bolt has the same area. Exactly. You're right. Yeah, so I think Radha has answered, because the geometry of the bolt is similar. So regardless of what material is there, the pressure distributions would be same, right? Because the pressure, if you make a free body diagram, right, the force is just pressure into area. It doesn't know the material, right? The stiffnesses will be different because of E, right? It doesn't matter whether I use aluminum or steel, right? If I apply P for a given cross section, the stresses will be the same. Right. So what in this case, what is happening is the compression which the bolt is doing, right? So this is just the compressive stresses. So it doesn't, material properties doesn't come into play. So you will have a very symmetric distribution, starting from highest pressure in the bottom and in the top, and just in the center you will have a nice broad area. So you will have kind of two inverted frustas. Frusta. Okay. And so if you have two different material, all you have to do is take each material separately, because then you have to estimate what is happening in each material. But if it's the same material, then there's nothing. Then you can just assume it to be like same. So all you can do is you can use the formula where 2T basically means is the entire grip length, and use that formula which we have for grip. Regardless whether there are 2 layers, 4 layers, doesn't matter. It will be the same. All it will do is for one portion, whatever you have computed, it will be half of it. The stiffness will be half of it, because it's 1 over K1 plus 1 over K2. So basically is equal. So basically if it is same, right? So 2 over K is equal to the total stiffness, which is, so Km will basically become K over 2. So stiffness will be half of whatever is there for one layer. Okay. What if one material yields? Then the two things will be different. So you are right. If it yields, then both will yield, right? If the material is same. But if material is different, then yielding properties can be different. But when you tighten the material, right, you don't want to let the material yield. By yielding, you are assuming that the material which is being pressed yields, right? So the material which is being, the 2 layers are yielding. You don't want them to yield. First thing, when you're tightening, you cannot tighten it so much that you have to, the material yields. You don't want to do that, because then you're failing the material by virtue of joining them. You don't want in any design process, right? You don't want your material to yield. You want your material to be nice and elastic zone. But you're right. If one material yields, then it will not be symmetric. You're very correct. Because after that, the pressure will, you cannot have this flaring thing, right? After yielding, but then what you have to assume is everything is still elastic. You're not yielding the material. Okay. Any other questions? So what we'll do is we'll still have the project meeting on Wednesday with all your group mates, and then Thursday we'll start the bearings, the rotary, the ball bearings, and the rotating element bearings will start. So this bolt we will stop here. I think we have covered almost everything. I knew it was a difficult thing today because I had to do a lot of derivations and solve the problem, and I don't know how to do, other than Mathematica, I don't know how to solve it in a distance mode. Classroom is much more interactive. We can do things, we can draw things. So that is a limitation here, but somehow we have to make do. Okay, thank you very much. So we'll stop here. Okay. Stop the recording.